Thank you very much. So I will speak about some other aspects about detecting gravitational waves and parameter estimation. So first, I give some basics of gravitational wave. So 100 years ago, shortly after Einstein proposed his equations, he linearized them and convinced himself that they admit gravitational waves propagating with the speed of light, with two polarization, and then the dominant effect, I mean the dominant contribution, or the first contribution, comes from the quadrupole moment. So here, here you have these two standard picture of these two polarizations. There's a ring of particles and how they are affected by gravitational waves. Okay, here you have the usual movie of inspiring binary system. All right, so next is the network of detectors. So now we have a worldwide network of detectors. Here I have the 4 detectors that are working. So these are these large-scale interferometers that their goal is, of course, the direct detection of gravitational waves. The property is that they're omnidirectional. And what they do, they collect a time series of data, where there is, of course, noise from the detector, and also the signal, possibly a signal. Something that, when these detectors were designed and built, was not very certain. Well, we have 4 classes of sources. Okay, they are supernovae, coalescing compact binary, stochastic signals, and periodic signals. So as you know, we have detected the signal from a black hole binary system, which is just a subtype of this class of coalescing signals, chirp signals. We expect to detect the other signals, but again, like with this first signal, there is no guarantee that we'll detect them. So the hopes are high. Okay, so we have these 4 detectors. I mean, these are the 2 4-kilometer LIGO detectors, and this detector detected the signal from binary black holes. This is the geo detector, which is part of LIGO project, and Tomek talked about this. And this is the Virgo detector, which was working for several years in this first era, where we had only upper limits, and now it's under still the upgrade is not finished. It should be finished, hopefully, at the end. Well, the detector should start working and collecting data at the end of this year. So we have 3 detectors. We have a network of 3 working detectors detecting, at least binary signals from binary black holes. Okay, so the next slide is the detector itself. So what you have here is, in some more detail, the layout of the LIGO detector in the configuration that it was working when it detected these binary black hole signals. Okay, the theory how that such a detector should find gravitational signals comes from this old paper by Pirani, where he considered a set of test particles, and he found that by this set of test particles we can measure the Riemann tensor. So these are considered as a theoretical basis for this type of detector. So this is a laser interferometer. We have a laser light, continuous laser beam. It was 25 watts, and then there are several systems that stabilize the frequency. In addition, of course, the light comes into the interferometer, it's split it into both arms, and then comes back. And here the interference pattern is monitored by the photodetectors. Very important is this additional mirror, which effectively increases the power. And of course, also here in the arms are multiple reflections, which also increase the power. So you see that the power from 25 watts goes to 100 kilowatts inside the arms, and finally through this signal, through this power recycling, increases to yes, I mean here the light goes in, it's around 25 watts. Then through the power recycling, it increases to 800 watts, and then through multiple reflections, it increases to 100 kilowatts. Then there's the signal recycling mirror, which is, well, the eventual purpose of this mirror is that by moving this mirror, you can tune this interferometer to particular frequencies, so you can make it sensitive at certain frequencies, but also it has an additional effect of stabilizing the whole setup. Well, in practice, what happens is that here the interferometer is held at the dark fringe, and then this is called what we have a lock, and then the control and what is the data at a certain voltage that keeps this detector at the dark fringe. So this is the data. And here is the sensitivity of the detector, which is measured by spectral density of noise. So this is essentially, some dimensionless quantity per root hertz. So it's like the amplitude at each frequency. Okay, next is here I have an old picture from the book of Hawking and Ellis, which is early 70s. This is when these people started to design laser interferometers. So this is the merger of two black holes, which was at that time considered. You'll see this trousers, the event horizon of the two black holes, and then they merge into one black hole. And here are some, because we have the area theorem, that the area of the black hole always increases. You can, in that book, Hawking and Ellis, they made some constraints on how much gravitational wave energy can be radiated. So it's always less than 50%, and less than this number when it's a non-spinning black hole. Then through some back-of-envelope calculations, making some Newtonian and special relativistic physics, you can measure how much energy is extracted, what's the percentage. So 1/30 of the energy of the systems can be extracted through gravitational waves. And this agrees more or less with very detailed calculation that we have now from numerical relativity that can model the whole merger, which, as we know, it's the in spiral phase, and then the merger, and then there are the normal modes. Okay, so the next slide is some basics of this gravitational wave from a binary system. So the gravitational waves, both the phase and amplitude, are determined by this combination of masses, which is called the chirp mass. So the amplitude is a relatively high power of the chirp mass. So it's 5/3. So it makes a difference whether it's a neutron star or a black hole. Here I refer to this first system that was detected, and we had this strain. This dimensional amplitude was roughly 10⁻²1. Then this is characteristic time for the evolution of the system. And then also the Fourier domain, the Fourier transform, which is we have a different dependence on the masses and chirps. This is per root hertz. And then the merger, which you can determine from the frequency, and when there is a merger, which we can estimate from the innermost stable orbit. The next thing is the detection of the signals. Then I give here a few fundamentals. The problem of detection of a signal. I mean, here we have a problem of detecting gravitational wave signals. The problem of detecting signal in noise, and this can be set up as a hypothesis testing problem. And the classic approach, which is now adopted, is the Neyman-Pearson approach. Jerzy Neyman is one of the members of Polish School of Mathematics, and he is somewhere here here on this poster. So the test is that you form a likelihood ratio, which is the ratio of the probability of distribution of the data when the signal is present over the probability signal when the signal is absent. And under this assumption, when the signal or noise, the signal is additive, so just added to the noise, not just kind of a nonlinear combination, and the noise is Gaussian, then this test is equivalent of correlating the data with the model of the signal. And in the case when the data are stationary, then you can express this correlation in the Fourier domain. I mean, then the spectral density is a well-defined quantity, and you have this Fourier domain. So essentially, it's like you multiply the Fourier transform of the data by the Fourier transform of the model, and you weight it by the noise in the detector. So that's the matched filter, correlating data with the model. Of course, usually you don't know the model exactly. It depends on the parameters. Then things are more complicated. You have to form a bank of filters. Then things are not so simple. Okay, so let's move to the next slide. And here is our detection about that we all know. And here on this plot, what I have, this is the estimate of the noise of the detector. And this is the value of the statistic that we use. It's not just the plain correlation, but it's just the sum of the quadratures of two correlations, cosine and sine. So it has an exponential distribution. When there is no signal, there is a noise. And this is the size of this detection statistic, which is essentially the signal to noise ratio. And this is for the data for the whole of this first run, so-called observational run one, when we had 3 signals. Okay, this is the first detection. It was the strongest signal. Then this is the second significant signal that the LIGO detectors detected. And of course, these are these two Fitzgerald papers where these results were published. And then there is this third signal. It's called, this one is called gravitational wave, and then there is the date. This is called LVT, means LIGO Virgo trigger. This signals was not as sensitive. So we had these 3 sensitive signals, and that was result for a search for signals for black holes, so for masses larger than 2 solar masses up to 100. Okay, the next things are some more details about these 3 signals. This is the first one, which was the strongest. You see there are just few cycles, then the merger, and then the ring down, which is just the formation of the final black hole and the normal modes, which also emit gravitational waves. Then this was the second significant one. You see it's many more cycles, maybe 30 cycles, then the merger. And then this one was this least significant. I mean, the third signal, which was not quite significant, so it's strongly suspected to be that it's really a signal. Okay, these are the models from the estimates of the parameters. Here one sees the things in the Fourier domain. So this is the sensitivity of the detector, and this is just the Fourier transform multiplied by square root of the frequency. So these signals, so these are our 3 signals, and here are some more details about the parameters of the signals detected. So here are the signal to noise ratio. These are the 2 very significant ones. Here is the significance measured by the probability. You see it's by probability, so-called false alarm probability. So the probability that that the data was consistent with noise is extremely small. So it's extremely very significant signal for these 2, and this one is much less significant. And here this is expressed in the usual sigmas. And here are the masses. So we see that the masses of the black holes that were involved, now it's quite a You know, these are the primary masses, and this is the final mass of the total mass of the black hole that resulted from a merger. So you see they range this initial masses from 7.5 to 36. So quite now we have a quite considerable range of masses. The first signal that was detected, which is this one, had unusually high masses. These masses were not observed in the black hole system that were usually observed, you know, in binaries, in systems with, you know, accreting stars with through X-rays, where you observed only masses up to 16 solar masses. So that was quite interesting and new. These are a new type of binaries. Well, not a new type, but, you know, much larger mass type of systems. Then here, okay, here's the final mass and the energy radiated. The distance, you know, these two significant signals happen to be roughly at the same distance. The other one was much further away, 1 gigaparsecs. Very interesting is, I will also give more details about the measurements of the spins. This is what Pankaj was asking. Something that is very interesting, that the final spin, the spin of the final black hole, that all the spins are around 0.7. I don't know whether it's a coincidence, but it's interesting that all three of them, they have this spin. So these are the fairly rapidly spinning black holes, not maximally, but rapidly spinning black holes. And here the errors are quite small, so this is quite reliable. It's interesting that, you know, they are the same. Another interesting details, I mean, a small detail about the estimation. You see here is the chirp mass. The chirp mass is to the first approximation, the quadruple approximation, determines the signal from the binary system, and this is best estimated from, you know, from this in spiral phase. So it's better estimated where you have more cycles, and it turned out really to be the case. Even though the signal was quite strong, the chirp mass had quite a bit of error, you know, around 2 solar masses, whereas for this second signal, where we had many more cycles, you know, the error on the chirp mass is much better, even though, you know, the signal to noise ratio is smaller. So, I mean, this shows certain consistency in the theory. Then I give more details about the spins. Okay, so they were concerning the discovery. Okay, there were these physical review letter papers, 2 papers describing it in detail, but we have also a paper which is in the archive, just submitted to Physical Review X, about the whole search for binary systems in the O1 data, observational one, and from this paper I extracted, you know, details about the estimation of the spin, when there are the errors, you know, there are there's certain bounds, there are some systematic errors. So what you see, that, okay, all these estimates indicate spinning black holes, because they're merging into this fairly rapidly spinning final black hole. As Tomek was saying here, the estimates are very uncertain, because just, you know, we don't have enough signal to noise ratio, we don't have enough cycles, but what is estimated is, you know, that these black holes, okay, they are spinning, rapidly spinning, but not exceeding, you know, the maximum, which is, of course, in general relativity, this is possible. You can have a spin greater than 1 in Kerr space, in Kerr solution, Kerr metric, but then you don't have a black hole, you have a naked singularity. And this is not excluded. This is, as we know, and maybe things that we'll be discussing in this workshop, we have this, you know, cosmic censorship hypothesis that in realistic case it's not the case, but it's not something is not proven, and something that can be verified observationally. and something to watch out, okay, for the time being. You know, we have this rapidly spinning black holes. Okay, I might mention that, you know, of course, the black holes are also observed by X-rays, where the spins are measured, and there also there you get maximal. You get fairly spinning black holes. Some of them spinning too closely to maximal spin for a black hole. Okay, so these are interesting observations, and we look out for more, of course, especially if we have, you know, one a day. If you know, the detectors reach the design sensitivity, this would be very interesting. The next thing I would talk about are something that also Tomek mentioned, which is very important, is the coincident observation with electromagnetic coincident observations with telescope, radio telescope. You know, LIGO and Virgo project, they set up collaborations, memorandum of understanding, over 70 projects, and this involved you know, telescopes, neutrinos, gamma rays, also some satellites observing gamma rays like Swift, Fermi, many projects, and they all signed a memorandum of understanding. This first event was followed by 25 teams. You know, the alerts were sent as agreed by the memorandum. So, you know, there was a lot of discussion because, you know, it was clear. Okay, we knew. I mean, that the people in the project, we knew that, of course, this must be black holes, but this information was still not passed to the electromagnetic observers. Also, you know, from black holes you don't expect in standard scenarios, you don't expect electromagnetic signals. So these alerts were set with some delays. You know, 2 days. I think 2 days for this first event and 1 day for the second event. It happened in December. So, of course, the goal is to send it much sooner, and there is an infrastructure to do this, because these gravitational waves with LIGO data are detected online. You know, the first signal was detected, and the second, they basically were detected within minutes after they arrived, within a minute after they arrived to the detectors, because we have very good algorithms and pipelines, and there are these signals are detected online, and there's sending them, you know, within 10 minutes is perfectly feasible. Okay, so the results of the analysis of these 25 teams were published. First of all, they were published in a publication. First, there was one paper, then was split into two. One giving, you know, just a short summary in Physical Review Letters, the other giving a bigger account. Also, the individual teams, they published their own results. And here's the sky map. You know, this is the sky map produced and the localization of the signal that the two LIGO detectors could produce. You know, with two detectors, you have basically one time delay, so you can estimate, you know, where the signal comes from on a ring. Then you have some additional information in the amplitudes of the signal, so then you can determine that it's more likely in certain two regions on the ring. But, you know, we really need to have three detectors to determine, to have a signal, you know, within, to have a much better location. And, you know, this is, okay, this is the reference where this was solved for the first time by myself and Jaranowski a long time ago. And these green tiles are the tiles that were covered by various projects. Okay, so the black is gravitational waves from LIGO and Virgo. So there were radio observations, which are red, there were optical, and there were X-ray and gamma ray. So quite a few observations. And none of them detected a counterpart, except one. So this was by by Fermi gamma burst monitor. This is a Fermi. It's a Fermi satellite. It's a NASA ESA project where there are on board there are two instruments. One is gamma ray burst monitor, and there's a Fermi other called Fermi Lab. Of course, this is a very big and very reliable project, and they claimed soon after we announced the first discovery, they claim a weak transient source, a weak coincidence, and this is something that seems very unlikely, and was the significance of this event is under debate. There are many references. It seems unlikely. Other GRB observations, Swift Integral and in Agila is an Italian project, they have not detected a counterpart, but I think the project, the Fermi GBM, they still claim, they still maintain this claim. I think the paper has not been published yet. I mean, it's got stuck, I think, in the referee process. So it's unlikely, but it's, as Tomek was saying, it's cost a lot of interest. So anyway, these coincident observations will be done. All right. So finally, I would like to summarize what's the meaning of this discovery. So of course, for the first time, the gravitational wave signal was registered by detector on Earth. For the first time, we saw a merger of two black holes into a single black hole, and so far, the data from these three signals, two basically guaranteed and the other one probable. They show that what we see is a coalescence of two black holes into a one black hole, which is consistent with the Kerr solutions of described by Einstein's general relativity. So the usual thing, of course, is that the gravity has been tested in an extreme gravity regime when the gravitational field is strong and dynamical. The velocities of these black holes were half of the speed of light before they merged. We have a new field, gravitational astronomy, and basically we have a third way of looking at our universe. One is, of course, electromagnetic observation. The other ones are elementary particle, like cosmic rays. The third one is gravitational wave. So it's a third way of looking at the universe, and this is one way why this discovery is is so significant. All right, so that's it. I wanted to say. Okay, thank you.
About the orientation of integral and other satellites in the time where the Fermi satellite tells that it find the gamma ray burst. Because angle of detection is about the quarter of the celestial sphere.
Yes. Yes, I don't know all the details, but all the results that are reported, they covered the field. I mean, the probability map of the signal that was given from the LIGO detector. So they covered most of it. It's all given in this all these studies. Whatever was covered, I don't know. This is. I don't know exactly what, say, Fermi and integral covered, but it's in the publications. I don't know.
I can comment that Fermi is an all-sky monitor, and integral has this. The higher you go to energy, the more all-sky it gets because the shielding is transparent. So this is quite an energy-dependent statement. What was expected? So I think that. Perhaps, for some localizations on this ring, the detection by Fermi and non-detection by integral will be consistent, but this is still under debate.
Yes, there is a discussion. discussion going on.
So, do we have any estimates on the rate of the binary events which will have electromagnetic counterparts, and once we have final configuration?
Are you talking about this Fermi?
No, I'm just asking, like in general, like if there are any estimates on how many events may have electromagnetic counterparts.
Well, how many events? So you know, from the black holes, all counterparts are speculative. From things like binary neutron star, this is something that there are estimates, and Tomek can talk about this more, but the most important thing is just to test whether it's really true that the merger of neutron stars is connected with gamma ray bursts, which is also not guaranteed. But there are estimates. There's a lot of estimates on the mergers, from various angles.
So do we know what is the rate? Like,
okay, so the rate of GRBs is that we observe in the universe is about 3 per day. Then with gravitational waves we observe only up to say 200 megaparsecs for binary system. So the spontaneous neutron star. So the expected rate of such events is quite small, because you see very tiny part of the universe. And this is very model dependent, whether that's 1 per year or 10 to minus 2 per year.
Yes, there is. I think there is a recent paper from maybe a week ago. They estimate how many these neutron star mergers can be observed, and there is a chance that they will be detected in the final run of when LIGO reaches its design sensitivity. So maybe in 2 years' time, there is a chance for such a detection.
So you mentioned that all of these final black holes have similar ratios of spins.
Mm-hmm.
Just from plain old numerical relativity simulations of say equal mass spinless binary black holes, simulations. I mean, what do those get for the final spin? Is it anything like that?
Pardon? Yes. From the simulations, whether there's anything.
Yeah. So in other words, if you just take the simplest case, equal mass originally spinless black holes, and they merge, what do you get for the final?
I don't exactly know this. 0.7, yes. I mean, this. Well, first of all, these results were reproduced by numerical relativity, but I don't know whether you always get 0.7, or maybe not. Yes. I don't remember. But anyway, this was tested. These cases, but whether it's always you get this is maybe an interesting question. Okay.
Right, but all I'm saying is
just the simplest case. I did non-rotating.
The number is what you get from the
simplest case. I don't know.
Things don't differ much from the simplest case.
I don't know how.
I think that 0.7 is the value that you expect if you naively take just the orbital angular momentum and put it into the final vector mass.
Yeah. Okay. Good. So that about as simple as it can be.
This makes this is all consistent.
Yeah. So okay. All right. Okay. Thanks.
What questions? Remarks?
Okay. Thank you.